Hi everyone, today is going to be the first video for Chapter 5 and we're going to be talking about graph sketching. And so really in today's video, what we're going to be doing is looking at graphs of functions and using some new vocabulary to describe that behavior and kind of chart out the behavior of a function so that ultimately when we're given the equation of a function or its derivative, we'll be able to sketch that graph. So today, like I said, we're just going to start by looking at a graph of f and describing its behavior using some new vocabulary terms. And some of them won't be new, some of them you'll be quite familiar with. So we're just going to run through this list, and I'm going to kind of talk about the definition for each term and then relate it to its position on the graph. So the first thing we're going to talk about is critical points. And those are just points on the graph where y prime is equal to 0 or it's undefined. And I'm going to write those in pink and we'll kind of highlight those points in pink as well. Now, one thing I want to talk about here, if I'm looking at a graph, I'll know that y prime equals 0 because there's a horizontal tangent at that point. Okay. The way I would know that that first derivative is undefined, if you think about when we talked back about differentiability, that derivative is going to be undefined anywhere we have cusps, corners, vertical tangent, or any kind of discontinuity. So holes, jumps, infinite discontinuity, things like that. So that's what I'm looking for my critical points. So if I look at my graph, I don't have any points where it's undefined, but I do have 2 points where I have my derivative is equal to 0. So that would be at this point here. There's a horizontal tangent there and a horizontal tangent here. So I'm just going to label, we're just looking at the x values of those points for now. So my critical points are going to be at x equals, looks like negative 1.5, and then x equals 1.5. So those are our critical points. The next type of point, the next term we'll be talking about is maxima of our function, maximum values or maxima. And that's just anywhere the graph has a high point. So let's say a maximum is a high point of a graph, and I'm going to say within a small interval. Okay, so the high point of a graph within a small interval, or we can also think of that as anywhere the graph has peaks. So now, I'm going to look at this function, and since we know we have a polynomial function here, I know this is going to go on down to negative infinity, and this is going to go up to positive infinity. So when we're talking about maxima, the first point that would be a maximum is right here. Because even though that point isn't the highest point on the whole function, within this interval, it's the highest point. So that would be a maximum. It takes on a maximum value at x equals negative 1.5. And sometimes you'll hear we'll call that a relative max, because it's not the highest point that the graph will ever take on, but in that area it is the greatest value. Now, when we talk about absolute maximum, that's where we're looking for where the graph, the highest point that the graph takes on at any point. So we're looking for, if I look over that whole, the domain of the whole function, where does it take on the absolute highest value? And so if I look at this graph, this was a maximum, but I can tell just by looking that that's not the absolute maximum because this takes on values that are much higher. However, this is just going to keep going to positive infinity. So I can't pick out an absolute maximum for this function. So it's important to note here that not all functions will have an absolute max. And I'm going to abbreviate just abs max. Okay, so I'm going to make a note here to say no absolute max. Okay, so now on the other hand, we can talk about minimum values or minima. And that's obviously just going to be the opposite of our max. So here we're talking about, and I'm going to do this in another color just so we're differentiating here. This is going to be the lowest value that the graph takes on within an interval. Sorry, that's super messy. But it says the lowest value that the graph takes on within an interval. Right? And we can think of these where valleys would occur. So here, this is going to be my minimum. It takes on a minimum value at x equals 1.5. And again, that's going to be relative. It's not the lowest value anywhere, but it is within that interval the lowest point. And just like with absolute max, we can talk about an absolute minimum. That's the lowest value. So the lowest value that the graph takes on. And again, in this case, my graph is going to keep going down to negative infinity. So I can't actually pin down an absolute minimum. So again, not all functions will have this. So not all functions will have an absolute minimum. So again, I'm going to make a note to say no absolute minimum. So now that we've got the concept of max and mins, we're going to talk a little bit about increasing and decreasing, which I know isn't new, but we want to talk about really what we're going to be talking about is some conventions when it comes to calculus. So in terms of calculus, we always said, let's jump back to pre-calculus. We know a function is increasing when it has a positive slope. And so for us in calculus, we know we're increasing whenever y prime is greater than or equal to 0. And just like when we talked about position, velocity, and acceleration, we said velocity was always a closed interval. We're always going to use closed intervals when we describe increasing and decreasing. And that's why we say when the derivative is greater than or equal to 0. And again, that's just by convention of calculus. So we're always going to use closed intervals to describe where I'm increasing or decreasing. So in my graph here, I'm increasing up to this point. So we have an interval that starts at negative infinity and goes to negative 1.5. And again, that's going to be closed. And then I'm increasing again over this interval. So from 1.5 to positive infinity. So then we're decreasing whenever y prime is less than or equal to 0. And again, we're always going to use those closed intervals. So in our example, if I sketch in blue here, that's where I'm decreasing. And I know that's happening from negative 1.5 to 1.5. Okay, so now from here we're going to go and look at some information that we get from the second derivative and see how that relates to our graph. So now we're going to talk a little bit about concavity. And so I'm going to write up here. Concavity here, when we talk about concavity, what we're talking about is the curvature of the graph. Okay, so the curvature of the graph. So for example, if I'm talking about concave up, right? Concave up is going to occur whenever my second derivative is greater than 0. And so here, since we're doing just strictly greater, for concavity we're going to use open intervals. And so if I'm concave up, it's going to look like this, where it's opening upwards. So sometimes I think it's helpful to think of concave up is like a cup. It'll hold water. So if I look at my graph and I look at this section here, this is looking concave up. That would hold water. So I'm just going to abbreviate for concave up here. And that interval, it's going to be open from 0 to positive infinity. So then on the other hand, we have concave down, right, which is where our second derivative is less than 0. Again, we're using open intervals here. And so it's going to look like this. And so sometimes we say concave down looks like a frown. Sad face. Okay, and so on my graph here, I probably should have picked two colors that look a little more different. But here I am concave down from negative infinity to 0. And so now what we have is what we call points of inflection. Okay, and for us, there's really two criteria we need to have a point of inflection. So first, there are points where the second derivative is 0 or undefined. In addition to that, it's points where the concavity actually changes from positive to negative or negative to positive. So in addition to the second derivative being 0 undefined, concavity must change in order for that point to be a point of inflection. So I can change from concave up to concave down or concave down to concave up, but without a change in concavity, I don't have an inflection point. And so here, this would be our point right here. I was concave down, and then at this point I changed to concave up. So that's the basic terminology we're going to be working with in this chapter. And so like I said, to start off with, we're just going to be looking at graphs and collecting all this information from a graph and organizing it in a table. Now, it's obviously easy to get this information in a graph, but once we've learned how to organize it, then starting in the next day or so, what we'll be able to do is get all this same information from a function, from the equation of a function, and use that information to actually sketch a graph. So here we go. I'm going to use lots of colors here so we can kind of make connections between all this information that we're grabbing. So first we're just going to list out the information that we get from our graph, and then we'll organize it in a table that's going to show us kind of, I guess in a table, more visual format, the behavior, what's going on with this graph. So I'm going to have lots of colors here. And here we go. So critical points. Remember we said critical points are where y prime is 0 or it's undefined. So quick scan of this graph, and now we're going to treat this as just having endpoints here and here as not continuing, even though it would most likely continue on. We're just going to look at this over a closed interval. So my critical points, I don't have any points where the derivatives can be undefined, but I can see a number of points where I have horizontal tangents. And so I'm just going to mark those here on the graph. Okay, and so it looks like those x values, and some of these will be estimations, and so if it's a little off, that's okay. We're just going to do our best estimation. So I have negative 0.7, it looks like, 0, 0.7, and then it looks like maybe 1.6. Those are my critical points. Okay, so now if I look for my maxima, looks like I have one here and here. And in this case, since I'm closed at this endpoint, I'm going to have a maximum value here. And in this case, even though it doesn't ask for it, I want to make a note. Since we're on a closed interval, this point is going to be the highest point anywhere on this graph. So that would be our absolute maximum. So again, it doesn't ask for that, but I just wanted to highlight that there. So now our maxima occur at x equals negative 0.7, 0.7, and then at our endpoint, 2.5. Now my minima, again, since I'm closed here, I'm going to take on a minimum value at this endpoint, this value here, and this value here. And again, it doesn't ask for it, but in this particular example, since I'm closed over this interval, this would be the lowest point I take on anywhere, so I would have an absolute minimum there. And so now my minimum values occur at x equals negative 1, 0, and we called that 1.6. All right, moving along, increasing, I know is where my slope is positive or my derivative is greater than or equal to 0. So I have an interval of increasing here, here, and then over this interval here. And we said we always write these as closed intervals. So I'm increasing from negative 1 to negative 0.7. Again, from 0 to 0.7. And then from 1.6 to 2.5. Decreasing is obviously those remaining intervals here. So I have two intervals where I am decreasing. Again, that's going to be closed notation. So now I'm negative 0.7 to 0 and 0.7 to 1.6. So this is all the information, right? I want to make a note here. This increasing and decreasing, right, is related to our first derivative. And so we have all closed notation there. When we start talking about concave up and concave down, that will be related to our second derivative. So let's take a look at that. So before I go to points of inflection, I'm going to look at my concavity. So the first thing I want to look at is where am I concave up? Remember we said that would be places where we can hold water. So I'm going to be concave up over this interval here. And then again from here to about here it looks like. And now when I'm estimating these intervals, I'm basically going to look, I know that I changed concavity in between this point, which we said was negative 0.7, and here, which was x equals 0. So I'm just going to call that where that change happens about halfway through. So this is negative 0.7, so I'm going to say at about negative 0.3, we'll call that. So I'm going to say I'm concave up from negative 0.3 to here we have a change between 0 and 0.7. So again, I'll say about, we'll call that 0.4. Again, whether you call it 0.3 or 0.4 isn't as important as long as you recognize where that behavior occurs. And then we have a second interval where we're concave up. Let's see, this was about from 0.7 to 1.6. So I'm going to call that about 1.2. And then we change from, let's see, 1.6 to 2.5. So I'm just going to call that about 2. Again, I'm not so concerned about the point that you estimated as long as you have the correct area where that behavior is occurring. And now I'm concave down. I don't know that I really have a different color. I'll just mark it in pen on these other intervals here, where we take on more of that kind of frown. And then you can see I'm starting to turn down here as well. So now I'm concave down from negative 1 to negative 0.3. Again, from, what would we call that, 0.4 to 1.2. And then 2 to our endpoint at 2.5. So then our points of inflection are just going to be the points where we have a change in that concavity. So anywhere I change concavity, so here, and here, and here, and here are all going to be points of inflection. So we have negative 0.3, 0.4. Our next one is at 1.2. And then I didn't really draw that well. It would probably be more like 2.1, but since we called it 2 just to be consistent, we'll call that 2 here. So that's all the information that we got from the graph. And now we just want to be able to organize that in a table. And really the point of putting it in this table is because eventually we'll only have a graph and we'll only have an equation, and we'll need to be able to generate this table to organize our information. And I realize we're over the 20 minutes. Just hang with me here and we'll get through this table. So I'm going to take all this information I have about my first and second derivative, and I'm going to organize it into a table. And I'm going to record the information I have about f prime, so increasing, decreasing, and f double prime, which is going to tell me about the concavity. And I don't know if I'll need all this, but I'm going to give myself a lot of space here. The first thing that I'm going to put on my table, I know my endpoint is negative 1, so that's going to be my endpoint here. And then I'm going to list my critical points. So I'm going to stay and I'm going to keep those in pink. So I'm going to have negative 0.7. I have one at 0. I have it 0.7. And I probably should have spread this out, but that's okay. 1.6. And then I know my endpoint is at 2.5. So we'll put that on here. So those are my critical points. Then I'm going to put on the information about my points of inflection. So I'm going to do those in purple. So now I have negative 0.3 to add. I have 0.4, 1.2, and 2. So pink are my critical points again, and then my points of inflection are purple. And so now, what I'm really describing here when I'm in f prime, we're going to list the information about where I'm increasing and decreasing. So again, I'm going to use my green for increasing. So we said we are increasing between -1 and -0.7. So I'm going to put a positive. I have a positive slope and I'm increasing. So that's how I'm going to record it in my table. My next interval was from 0 to 0.7. So I was increasing over those intervals. And then 1.6 to 2.5 is also intervals of increase. And so you can see I'm kind of changing whenever I hit a critical point, those points in pink. If I add in my decreasing, I'm decreasing from -7 to 0. So I have a negative slope. My first derivative is negative, which gives me decreasing behavior. My next interval is from 0.7 to 1.6. So you can see changes from increasing to decreasing always happen at these critical points. At the critical point of -0.7, I change from increasing to decreasing. At my critical point of 0, I change from decreasing to increasing, and so on. So those changes in that behavior happen at those critical points. Now I'm going to look at concavity, right, which is what my second derivative tells me about. It tells me about the concavity. And so again, I can look at my graph or I can look at the intervals that I charted out here. So we'll start with concave up. From -0.3 to 0.4, my second derivative is positive, and I'm going to sketch it. It means I look like this. I'm concave up. I'm also concave up from 1.2 to 2, so I'm going to add that information here. Everywhere else, I'm concave down. So from -1 to -0.3, so I have a frown type behavior. From 0.4 to 1.2, and then 2 to 2.5. And so here you can see my changes in concavity happen at these purple points, which is what we said. Those are my points of inflection, and we said those are the points where I'm changing concavity. So for right now, this is what we need to be able to do, is to take all this information that we have about the first and second derivative, take that information from a graph, and turn it into a table. Ultimately, where we're going is we'll just have an equation. We'll generate all the same, so we won't have the graph anymore, but we'll generate all this same information using the function, and then we'll be able to sketch this graph. So that's quite enough for today. You'll get some practice with this in class tomorrow. Bring your colors.